Alright, good morning everybody. Happy Wednesday. I know I'm a little late posting this lecture. I had a doctor's appointment yesterday and I had to take my cat to the vet. So, because of that, I will be giving y'all an extra point on your next quiz, and the quizzes are worth 10 points, so that's like an extra 10% on the quiz grade. So, hopefully it won't be too long today. I have some good news that I would like to start off the class with, some optimism. So I've been saying it will never rain again in Oklahoma, but as you can see on the SPC Day 1 convective outlook, there is a chance for thunderstorms. And I'm very grateful. So I thought maybe we would start with a quick forecast. So you can go to Pivotal Weather to look at what the forecast looks like, and then you click on Models. Okay, so what should we start off looking at? Typically, I start off looking at the 200 or 300 millibar heights to look at the upper atmosphere, because remember, the lower the number, the higher up in the atmosphere you are. It's the summertime, so I'll check 200 first. Okay, so you can see there's this. Let me also change the model run. So I'm using the GFS, which is a long-term forecast. The balloon launch becomes valid at 0Z. So I will click that for more accurate. And you can see we have this ridging pattern, this upper level ridge, that's been persistent. So you can see the huge ridge, but embedded in it is a short wave. So a little trough, and that's good for generating lift. So we have a little trough up north, and we know at the exit region of the trough, so the right hand side, we can get some severe weather. So I'm going to switch this to the forecast loop, and we can kind of go out in the future. So we have this ridge, but it's starting to push out, and a trough is moving through. Now, because it's the summertime, the trough is more north. In the winter months and the springtime, and even the fall, you'll see these troughs meander south, and that's equivalent to where the jet stream is. So this is the polar jet, and this is what's going to bring severe weather in, and again, on the right-hand side of the trough is usually where we see severe. So you can see it kind of pushes down, and we get a bit of that flow. So it's not going to bring anything severe here. We're not in the region, the exit region of the trough, where we usually get that upper level divergence. Upper level divergence creates a vacuum and leads to a surface low. So the severe weather threat is probably mostly up here, but because we're changing the flow pattern to look more trough-like than ridge, which has been persistent, we might see some rain today. Now, looking out in the future, of course, after a few days, the accuracy really goes down. We have some zonal flow, so it's more ridge-like than trough-like, so I wouldn't expect too much weather. But zonal flow is where the flow is more of this straight line instead of ridged or troughed. So sometimes it can bring a little bit of weather. Usually not severe, but if you can get the wind speeds fast enough, which it looks like we do have some faster wind speeds, you can get some weather. Okay, and then again, more good news, we get another little trough pattern. So hopefully in the future we can get some more rain this summer, and then of course, like later on, it's not going to be accurate this far out, but the GFS is predicting more of this ridge-like pattern, so the heat wave comes back. But hopefully we can get some rain today. That would be really nice. Let's look at the day 2 outlook. So sorry, this is the categorical. See, okay, tomorrow we also are in the T-storm region, and we had that divergence up here. We also have a chance for some thunderstorms down in the south. So let's look at that. So this is the area. So there is some divergence down here. Let's look at the 300 millibar level. Yeah, so you can see even lower in the lower levels, you kind of get a little bit more of the divergence of the winds. Plus, in the south, you can really a little goes a long way because there's so much moisture, and there's more of a ridge-like pattern. Now, you can also look at precipitation type and rate, and you can see there's a little spotted precip. So yeah, so you can see in like the Oklahoma, along the Red River between Oklahoma and Arkansas, there's a pretty good storm forming, and then there's just some light rain it's predicting, so that's good. And then this is like the ridging time, so there's not really any rain, but in the future there might be some spots of rain later on in the week. Fingers crossed. So hopefully that will break some of the heat. Water is good for mitigating heat because it's harder to change the temperature of water. So fingers crossed. All right. Now that we've done the brief forecast, let's do a review of last lecture. So if you remember what we talked about last time, we talked about winter storms. And we talked about how those extratropical cyclones that form from the troughs are what brings in winter storms as well. We talked a bit about wind chill, and wind chill is just the temperature and the wind speed combined. So the wind speed is an important factor because it evaporates the water off of your body and it cools you off much faster. And then we talked a bit about winter weather safety, frostbite and hypothermia, and ways you can mitigate that. So today we'll be talking about tropical cyclones, and we'll also talk about weather radar. So tropical cyclones. What is a tropical cyclone? A tropical cyclone is a low pressure center that forms in the low latitudes. So this is low latitudes, meaning around the equator. And this contrasts with the mid-latitude extratropical cyclones, which form in the mid-latitudes. So the mid-latitude wave cyclones are associated with tornado outbreaks and the hurricanes and stuff. Tropical cyclones are associated with lower latitude, and they create like the tropical storms and hurricanes and stuff like that. So let's talk about some of the categories. So a tropical depression forms at 39 miles per hour less than 39 miles per hour. So you get a tropical depression and it has a little bit of rotation, but it doesn't have an eye. Tropical storms form the second that that wind speed hits 39 miles per hour. And there's something incorrect on this slide. That's not supposed to say 75. It's supposed to say 74. So less than 74 miles per hour. Strong rotation. I would argue that there's not an eye in a tropical storm, really. Like there's a pseudo eye, like it kind of looks like an eye, but it's not really an eye. A hurricane forms at 75 miles per hour, or 74 miles per hour. And this is going to be a quiz question. That's why I point out that it's incorrect on here, because I want to make sure that you know that a hurricane forms at 74 miles per hour. And those are sustained winds. So not just wind gusts. Like the wind has to be 74 miles per hour for quite a bit of time. So 74 miles per hour has enough rotation and wind speed to form an eye wall. So that's why the threshold is 74 miles per hour. And the meaning of the word sustained is 1 minute average winds 10 meters above the ground. Okay, so let's talk a little bit more about tropical cyclones. They may form in the low latitudes, but they don't stay there. So they usually form off the coast of Africa, and they move in these easterly. They move in these easterly waves. So there's these waves coming off. I can show you this. Let's look at this really quick. So this is a website called Earth Null School, and you can see wind patterns. So let's go up in the atmosphere. We're at the surface right now. So I'm going to go up to 250. So as you can see, off the coast of Africa here, you get these wave patterns, and this is really where they form. So they form in like, it's this a similar thing. They'll form in like these ridges and troughs, and if you can get a storm to form right here, if it can make it over this first hump, it will usually make its way over to the United States. So this is where they form, off the coast of Africa, and they're pushed by this current here, and then they go up the Gulf, or they go up the Atlantic seaboard. So they usually move from the low latitudes to the mid latitudes. And when they move to the mid latitudes, usually that's when they they die. So they can still like cause some really good damage in the mid latitudes. An example of this was Hurricane Sandy. Hurricane Sandy had an incredible amount of power, caused a lot of damage. Similarly, like Hurricane Katrina and stuff like that. So they rotated north, and to be honest, a hurricane is more powerful when it is dying than it is when it's getting stronger, because when a hurricane starts dying, it just unloads all of its rain, and because it doesn't have the support anymore to hold all of that up, so it can just start dumping rain and create really bad flooding. So usually it's not a good thing when a hurricane is like a category 5 and it quickly shifts to a category 3 right before making landfall. That's not a good sign. Okay, sorry. So, what are the 6 necessary ingredients for tropical cyclone formation? Well, the importance of this, the important note to make about this is that these are just ingredients that you need. If you don't meet these, you can't form one, but just because you have these ingredients doesn't mean it's going to form. It just means the conditions are right for formation. It doesn't necessarily mean one's going to form. So here's the ingredients that you need. The first one is a pre-existing low pressure area. So like we were talking about, off the coast of Africa, you need a tropical wave or an easterly wave or a tropical disturbance. So it provides a cluster of rising air and thunderstorms. TC stands for tropical cyclones. The second thing you need is warm sea surface temperatures. This is really important. If you don't have the sea surface temperatures to sustain a hurricane, they're not going to form, because that's where they get most of their energy from. And that's why we really see hurricane season in late summer, because that's when the water is the warmest. So, rule of thumb, sea surface temperatures greater or equal to 80 degrees Fahrenheit. So it creates warm and moist air parcels that give a tropical cyclone its energy. And the parcels are low density and rise rapidly, and they reach saturation easily. And that's just because it's off the water, and the water is evaporating really rapidly. And so it's just fuel for the hurricane or tropical cyclone. And the warm surface ocean water, it needs to run rather deep. It needs to be about 200 feet deep. And that keeps it warm even when the strong tropical cyclone winds stir up the ocean and cause upwelling. And upwelling is when colder water rises from the deep ocean. So the fourth ingredient is rapid cooling of the troposphere with height. So this creates the unstable environment when warm, moist air parcels can rise rapidly. So the air parcels, when they're in a cold environment, the parcels will be warmer than the environment, and warm air likes to rise, so that's good for tropical cyclone development. Calm winds through the depth of the troposphere. So you need weak vertical wind shear. And what happens is if you have strong vertical wind shear where the winds in the upper levels are moving a lot faster than the winds at the surface, the updrafts will tilt and then they will fall over, so you can't get that hurricane development, that strong storm development. So you need the air parcels to rise rapidly and the energy to stay concentrated around the center of the cyclone. So they form in the absence of jet streams. Now, when they get to the United States and they're making landfall, they can combine with the effects of the jet stream to create a more powerful storm. But during formation, you don't really want the jet stream interfering in any way. And the jet stream can steer the storm. And they form between 5 to 30 degrees north or south of the equator. So you need greater than 0 Coriolis, so it can't be on the equator because that Coriolis creates that spin. The Coriolis on the equator is 0. So if you get above the equator, you have some Coriolis, so you can meet, and if you meet the other conditions, you can still have some spin if you get up to 5 degrees. So what is vertical wind shear? Vertical wind shear is the change in wind speed or direction with height above the ground. So there's 2 different types of wind shear. They're very important in weather forecasting. So speed shear, it's this one on the right. So this is the winds increasing or decreasing with speed with height. So this is vertical wind shear that is increasing with height, speed shear. So at the surface you have these 5 knot winds, and aloft you have 30 knot winds. So there's always going to be some wind shear, speed shear, because the surface has friction and aloft has no friction. But if you can get fast wind shear, moving off the topic of cyclone or tropical cyclones and moving to extratropical cyclones, in a trough, if you can have these fast wind speeds aloft, it creates like a vacuum. It creates a low pressure, and this is due to the Bernoulli principle. So air that's moving faster has a lower pressure, so that will generate rising motion. But not on tropical cyclone formation, because you really want that updraft to be formed by the warm water, and you don't want it to tilt. It doesn't really matter that much in the extratropical cyclones, because that's kind of how they're formed. So let's talk about directional shear. This is winds changing direction with height. And this is good for, this directional shear is good for storm formation as well. Again, talking about extratropical cyclones, not tropical cyclones, really fast. So if you had a profile that looks like this, at the surface the winds are coming from the southeast, so it is a southeasterly wind. This is going to pull in like Gulf moisture. If you think of like this was the United States right here, if it's coming from the southeast, that means at the surface you're getting this warm Gulf air. If it's coming from the southwest, it means in the mid-levels you're going to have this dry air. And then aloft you have westerly winds, which is going to be continental polar air. So this surface parcel is going to want to rise above these because these layers up top are colder and denser. So this is a good shear profile to have when you want severe weather that is extratropical. Wind shear is not good for tropical cyclone development, though, because it's a different formation process. So what we don't want is for our updrafts to tilt. It's like a very delicate process to form a hurricane. You kind of want to leave it undisturbed. And you want to get them rotating just by the Coriolis effect alone. You don't really want to get them rotating by speed or directional shear, because what's most important in the hurricane is that upwards rising motion that forms from the surface moisture. So I showed the tropical waves on the Earth.NOLA website. Tropical waves and easterly waves, they're elongated areas of low pressure that persist for at least a day. So you have a low pressure area, a storm starts forming. They're affected westward by those easterly trade winds. So that was the ridges and troughs I was showing that move east. And the low pressure creates a cluster of weak thunderstorms off the coast of Africa, and that's where the tropical cyclone gets its start. And as it moves east, or moves west, the storm can start to intensify, especially if it gets up in the Gulf, because the Gulf of Mexico is really warm. It just feeds off of that. So, in the Atlantic, the tropical waves form off of Africa's western coast, and in the Pacific, the tropical waves form off the western coast of Central and South America. So, it's like a similar process. Are they going to talk about invest? Okay, when something becomes an invest, it means that it may become a tropical cyclone. And when something's labeled as an invest, it means that the hurricane hunters, which are out of Biloxi, Mississippi, they will fly out of Keesler Air Force Base and they will go into the storm in their airplane. And it's really cool. A lady gets out on the wing and she throws these instruments out into the storm while standing on the wing, and they take a bunch of measurements. They're like these big metal boxes, well, kind of smaller metal boxes, and they will land in the water, and then they will dissolve to a tiny piece of metal that's about the size of a $50. So it's pretty impressive machinery. They're really expensive, and they just throw a bunch of them into there to figure out if it's going to form a hurricane. So, tropical waves, they don't have circular shapes yet. They don't have rotation. But as they strengthen, they start to form this closed low pressure center, and the Coriolis effect causes the winds to rotate around this low pressure system. So a tropical depression forms when that low pressure center develops within the tropical wave. So only 10% of tropical waves become tropical depressions, and they're numbered. They're not names. So a tropical depression, there's more tropical depressions than like tropical storms or hurricanes. So they only have a limited number of names, and so they just give these numbers, and then once it becomes strong enough, they'll give it a name. And it's tough to get all the ingredients together to get a tropical depression, but late summer is ripe to get these. Another problem that you can have with getting these tropical depressions is Saharan dust. You can get this dust off the coast of Africa, and not good. It really limits the formation of the tropical depression. It dries the atmosphere out. Okay, tropical waves cause most but not all tropical depressions. Tropical disturbances are clusters of thunderstorms that form along the ITCZ. So remember, intertropical convergence zone? That's that zone where the two Hadley cells meet, and usually it's around the equator. But it can meander north and south depending on the season. And what happens is those two air masses converge at the surface, and it can create this upwards motion. And if they go over a baroclinic zone, so a zone of low pressure, they can strengthen and they end up forming a closed low pressure center, and then the Coriolis effect get them to rotate. And once that low pressure system forms, that's when it's classified as a tropical depression. Not typical. I would say that the vast majority of tropical depressions form from those easterly waves off of Africa. Okay, so they have some labels here. I'll point them out. So here's two tropical disturbances off the coast of Mexico, and these are thunderstorm clusters along the ITCZ. So you can see it right here, this band, and that's where the Hadley cell is converging. So this was taken probably in the late summer. Yeah, it was taken on September 22nd, 2017. So the ITCZ moves north during the summer months here. And so this is that convergence of the two cells. And it's creating these updrafts. Green here, this is post-tropical cyclone Jose. So post meaning it's not anymore, but it was. So what happened was it probably moved off the coast of Africa, and then it got sucked up by the jet stream, and now it's remnants, and it's going to be shipped off to Europe. In blue, we have Hurricane Maria, which was a very powerful storm that hit Puerto Rico. As you can see, it's hitting Puerto Rico at that moment, so yeah, not good. Maybe Puerto Rico's, I think this is Puerto Rico. It was not a good storm. It caused a lot of devastation. I think it hit as a Category 5. And then yellow, Tropical Storm Lee. I don't really remember that storm. I was so worried about Hurricane Maria, I didn't even notice, but yeah. So, it didn't, what happens is if you get like a hurricane right here, sometimes it will take up the energy, so it will use that surface heat as fuel, and then storms that form behind it, sometimes they're weaker because they don't have the necessary fuel. Now, it's not always, but it's typical for the environment to be kind of messed up. Also, we talked about how the water gets stirred up. So if it's stirring up the water and putting up cold water, it can be harder to get that cyclone development. So here is the naming conventions. Let's see. I think we already got Bonnie. They will never have my name, I don't think. Yeah, no Kendall. So what can we be expecting this year? Danielle, Earl, Fiona, Gaston, is that Hermione or Hermione? I'm going to say Hermione. I kind of like Harry Potter. Ian, Julia, Carl, Lisa, Martin, Nicole, Owen, Paula, Richard, Sherry, Tobias, Virginie, and Walter. So that's what's to expect this year. So yeah, we talked about how they have a closed low pressure center and a slight rotation, but it's not low enough to form an eye. And it's not really like, we don't measure it on low pressure. We measure it based on wind speed, but the wind speed is enhanced when you have a deeper low. So you need the pressure to get low enough to get that wind speed up. If the other 5 ingredients are present and not the low pressure, within a half a day to a couple of days, a tropical depression may strengthen into a tropical storm. Once it becomes a tropical storm, that's when it's given one of these names. And this WMO, the World Meteorological Organization, they have lists of names for various regions around the world. So these are just the the Atlantic hurricane season, but they have a different list of names for the Pacific. And this list repeats every 6 years, except for names that have been retired. So, like, there's never going to be another Hurricane Katrina. There's never going to be another Hurricane Sandy. They retire names when there's been a strong storm. Honestly, whoever comes up with these names, they should hire me. I think that would be a really fun job to, like, look at baby names and, like, come up with new names. Like, who is naming the Hurricane Edward? Like, I don't know. I think I could come up with some interesting names. Yeah, so this list is for the Caribbean, the Gulf of Mexico, and North Atlantic. Sorry if your name is Eduard. I'm sorry. I don't think any of you are named that, though, because I looked at the class roster, so. Okay. Sorry if your family's named that, though. It's a nice name. Okay. So, here's a little, graphic that we're gonna go through. So, blue, big rectangle, this is the ocean. So, what happens? It's warm, and it heats this air above it by conduction. So, it's conducting. They're touching. That's what conduction means, heating by touching. So, this very shallow surface layer right here, just the contact layer, is heated by conduction. Then, water from the sea surface evaporates into the warm air. So you have this warm air mass, warm and moist air mass that forms near the ocean surface. This is the energy source for this cyclone. So as you can see, if you get like warmer water, it's going to be better for this formation of this warm, moist air mass. Then it's not really, it's really like not dense at all. Like it's very buoyant, and the area in the troposphere above it is cool. So this is an unstable air mass, and it's going to rise rapidly. And if you have like minimal wind shear, like, it's gonna be able to sustain itself and keep on rising, and it will stay upright. Like, if you have like strong wind shear, meaning like the wind speed up here is fast, it's just gonna topple over. So you want the parcel to rise up in a straight line for tropical cyclones. So what happens is when you get this rising motion right here, it kind of creates a vacuum because this air is rising, it's leaving, so it has to fill in. So it creates a low pressure center next to the ocean surface at the base of the updraft. Once this low pressure center forms, it's classified as a tropical depression. So I guess at this point before, this is when it's like an invest, and then this is when it becomes a tropical depression, when you get this closed low. So we have PGF, pressure gradient force. It causes the surface winds to strengthen and converge onto the low pressure center. So yeah, you have a surface low, and then the air around it wants to fill it in. So it pulls in more of this warm, moist air from the water around it. So you have these other air masses around that are also warm. So it's like feeding itself, and it's kind of creating a machine. This will strengthen the updraft. And this strong surface wind can create choppy waves and sea spray. And when you can get like a strong wind, it creates manual evaporation. So you can get evaporation from like temperature, but you can also get it from manually forcing evaporation. So like if you get sea spray and stuff like that, it basically forces evaporation. That's why it's like whenever you're wet and then you turn on like a fan, or you get out of the pool and it's windy, it's very cold because it is manually evaporating water off of you. And so that's kind of what happens here. Like you get even more evaporation, and yeah, so it fuels the storm even more, and it will strengthen the tropical depression. So then, what happens is it forms a high pressure aloft, and the reason why is because all of the air is kind of piling up here, so you don't have much air down here, and you have a lot of air up here. And also the stratosphere, which is above the tropopause, is very stable, so this air can't push past it. Like, it would like to continue to go up, but it can't because the temperature increases at the tropopause. So you have a high pressure and the air starts pushing outwards. So this is kind of like we're looking at the core, like the eye of the hurricane. Well, it's not a hurricane yet. But, you know, this is what would be the eye. And aloft, this is happening in every direction. So there's some pointing that way, like behind it. There's some pointing towards us. But yeah, it spreads out in every direction aloft. And finally, as it moves outwards, it cools down, and it becomes more dense than the surrounding air. And so it starts sinking down, and as it sinks, it warms back up again, and this creates the circulation. So you have circulations on all sides that look like this. Yeah, this is called, you can see this in cars. This is a heat engine. It's called the Carnot cycle, Carnot, Carnot. Yeah, and it just looks like this. It's a pretty simple math equation to figure out how the energy transfer happens here, and you will do that in your thermodynamics class. So, condensation really releases the latent heat, so it hits the LCL, the lifting condensation level, and it condenses into clouds, and this will strengthen the updraft because condensation is a warming process. So if you don't have that wind shear, that vertical shear profile, the heat is going to stay closer to the center of the storm, and you want the heat to be in the center of the storm because this is kind of like the main fuel center. So this is another main energy source for the storm besides the warm, moist air mass at the surface. It's also the condensation of water vapor into liquid at the LCL. There is the clouds. So yeah, the rising air parcels in the updraft, they're very warm, they're moist. They quickly reach saturation. The water vapor begins to condense. So this creates the rain, clouds, and thunderstorms. So it's hundreds of miles across, and it has strong winds. The size of the system means that the Coriolis force causes it to rotate. also the wind speed. So it's like the size of the system and the fast wind speeds lead to the Coriolis effect taking place. So in the northern hemisphere where we are, we'll see these systems rotate counterclockwise, and in the southern hemisphere, we'll see them clockwise. And once you get those wind speeds to 74 miles per hour, this is when you get that eye wall formation. So the rising warm, moist air, divergence aloft, and the concentrated latent heat release in the updraft creates a positive feedback loop. So it causes the tropical cyclone to strengthen. And then the pressure in the center keeps getting lower, and the circulation continues to spin faster. If the necessary ingredients persist for a couple days, the cyclone will become a tropical storm, and then it will become a hurricane. So 50 to 70% of tropical storms become hurricanes. So this is the Saffir-Simpson scale. This is what we use to categorize hurricanes. It's correct on here. See, category 1 starts at 74 miles per hour. Oh, I just highlighted this whole thing. Okay, so it's based on sustained wind speeds. So all hurricanes begin as category 1 once it hits that 74 mile per hour sustained winds. And then the wind speeds keep picking up. And then once you hit category 3, so 111 miles per hour, this is when it's considered a major hurricane because they cause intense, widespread damage and have a higher risk of casualties. I don't recommend sitting through a hurricane, but I mean, if you're above a category 2, like, you should probably leave if you're on the coast. Like, I would evacuate, I would probably maybe at most a category 1. I might even go inland for a category 1. I don't know. But it's not a good situation to be in. So yeah, once it hits category 3 though, the risk of casualties goes up significantly. Okay, next PowerPoint. Okay, so we just talked about tropical cyclone formation. And we talked about the 3 levels to the tropical cyclones. So the weakest is the tropical depression, which is less than 39 miles per hour sustained winds. Then once you hit 39 mile per hour sustained winds, we form the tropical storm. And once you hit 74 mile per hour sustained winds, that's when it forms a hurricane. And this is 10 meters above the ground. We had 6 necessary ingredients for tropical cyclone formation: a broad low pressure, warm ocean surface, warm ocean top layer, a cold or unstable troposphere, or a cold troposphere that creates an unstable air parcel, calm winds, and it has to be in the low latitudes. And then we talked about how they form. Yeah, it was a lot of information, and the most important thing is knowing the 6 ingredients that creates formation. So let's talk about factors that inhibit tropical cyclone formation. So inhibit just meaning things that don't allow it to form. So things that prevent formation. 1, the lack of tropical wave can prevent this whole process. Yeah, so that thing off the coast of Africa that we're showing, if you don't have those, those are kind of fuel the whole thing. So if you don't have that, it's probably not going to form. 2, if you have cool sea surface temperatures or a shallow warm ocean surface layer, it can prevent that parcel from warming up enough to rise freely. If you have dry air, it prevents the air parcels from reaching saturation. So you want the air to be really moist, so once it hits the LCL, it can create those clouds and thunderstorms. 4, an inversion, meaning that the air is increasing in temperature with height. This creates a stable environment, which prevents the air parcels from rising, because remember, you want the air parcel to be warmer than the environment so it can rise. 5, strong vertical wind shear. especially in a jet stream. They can prevent the central updraft from remaining upright. So, parcels rise less rapidly and they weaken the storm, and latent heat is dispersed over a greater area, weakening the storm. So, less than 10% of tropical waves become tropical depressions. So, you have to get all of these ingredients together in one place. Very delicate process, and you have to have everything correct at the same time. Many of these poor conditions tend to prevail in the mid-latitudes, so once you get to the 30 degrees line, it's harder to get it. So that's why tropical cyclones, they eventually weaken when they move from the low latitudes to the mid-latitudes. Additionally, greater friction over land than water slows down the tropical cyclones and weakens them further. So remember, we formed that low pressure because of the wind speed. Well, we had the warm, moist air mass that created that low, and you're not going to have that warm, moist air anymore because you're over land. And then there's friction, so that creates a force that slows it down. And then the low pressure weakens because you don't have that upwards motion, and so wind speeds will weaken. Ingredients for tropical cyclone formation are consistently found in tropical cyclone basins. So they're far enough from the equator for the Coriolis to be sufficiently strong. They're dominated by the calm trade winds and weak subtropical jet, and they have warm sea surface temperatures. So this is the one I was talking about. All of these are tropical cyclone basins, so tropical cyclones can form in all of these, but the ones that we're predominantly concerned with for the United States that make landfall in the eastern half of the United States, see, they form off of the coast of Africa and they move into the Atlantic or the Gulf of Mexico. Yeah, so here are the names. So we're concerned with the North Atlantic Basin, but these are all the other basins. You can read these if you're interested in their name. Also, with the Eastern Pacific Basin, I've seen hurricanes that have hit Hawaii before that have formed from there. But yeah, you can get these to all form tropical cyclones. So they have different naming conventions based on where they are, but these words all mean the same thing. So in the North Atlantic and Eastern Pacific basins right here, they're both called hurricanes. In the Western Pacific Basin, they're called typhoons. And then in all of these other basins, they're just called a cyclone. But they all mean the same thing. And tropical cyclones form in the warm season, the summer and fall, in each hemisphere. So it's going to be opposite season for this southern hemisphere storms than it is for the northern hemisphere. So there's no southern Atlantic basin because South Atlantic is characterized, so down here. There's cool sea surface temperatures, there's a lack of tropical waves, and there's typically strong westerly winds. So westerly is coming from this way. So they're rare, but I guess they're not impossible. They had one called Cyclone Katarina in March 2004. But yeah, it's not typical to see tropical cyclones down there. On average, 80 tropical cyclones occur globally each year, with 66% of them occurring in the northern hemisphere. And the most active basin is the Western Pacific, and the least active basin is the North Indian. So let's look really fast. So Western Pacific right here. So yeah, you get a lot of typhoons and stuff. I think they're typhoons forming right here. This is the most active. And then, what's the least active one? North Indian. So, right here. So, you get less of them right here. Okay. Some graphics. So, in the North Atlantic Basin, what we're primarily concerned with, on average, they get 11 tropical storms. 6 of these are hurricanes, and 2 are major hurricanes. In the Eastern Pacific Basin, where this is like include like this like the named systems, like we're subtracting here. So there's 11 named systems, and of those 11, 6 of them are hurricane, and of these 6, 2 of them are major hurricanes. But in the Eastern Pacific Basin, where we were talking about, where it has a lot of storms, you get 15 named systems, and 9 of them become hurricanes, and 4 of them become major hurricanes. But I think this number might be going up. I don't know. It might be a climate change thing, but I can't prove that, so we're not going to say that. Yeah, it's a little unscientific to say, oh yes, there are so many more hurricanes right now because of climate change. Climate change is real. Climate change is provable. But it takes a long time to measure the climate, and this is weather. So we're going to have a lot of years of information and repeated patterns to be able to attribute it to climate change. So it's quite possible that there will be more hurricanes because of climate change. It would make sense because the sea surface temperature would be warmer. But we can't say that like a certain year had more hurricanes because of climate change. Tropical cyclone basins. So in the North Atlantic and Eastern Pacific basins, tropical cyclones typically start their lives moving east to west with the trade winds. So that's those winds that we were showing on Earth Null School. So as they enter the mid-latitudes, the westerlies generally steer them north, and then they move back east. So this east movement is because they get caught up in the jet stream, the Gulf Stream, so it picks them up and it moves them to Europe. And this is like a bunch of spaghettis. This is like a really weird map. It's actually kind of creeping me out. But these are all the tropical cyclone tracks from 1851 in the Atlantic. Does this like weird anybody else out? Like, I don't know. It kind of looks like hair or like something. I don't know. It's making me a little uncomfortable. But yeah, that's a lot. There's a lot of them. Okay, hurricane forecasting. Hurricane forecasting is incredibly difficult. In my opinion, it's more difficult than forecasting for like a extratropical cyclone. So hurricane forecasts, they're issued by the National Hurricane Center, NHC. So you can just Google National Hurricane Center and you can get all these graphics, and you can find these. So they create a cone of uncertainty. So they start at a point and they widen the cone as time goes by because it becomes more and more uncertain as the days go on. So the solid white part of the cone down here, this is 1 to 3 days in the future, and then it expands out and it's like 4 to 5 days in the future, and it's like a stippled white part of the cone. It also plots where the center of the cyclone would be if it stayed in the middle of the cone. The center has a 60 to 70% chance of being anywhere in the cone and a 34 to 40% chance of being outside of the cone. Yeah, it's really tough. Like, these forecasts are usually, they're like pretty good, but our knowledge of hurricane forecasting is limited by our products that we use. So the cone is your best bet. The National Hurricane Center employs a lot of very talented scientists that do their best, and usually they're pretty good, but the cones do change pretty frequently, so you have to go back and look and see how they're changing. So the cone tells you where the tropical cyclone is most likely to go. For modeling, the models the United States have created, we don't know why. Our weather models, like, kind of suck compared to the European models for forecasting, especially hurricanes. So usually I'll use, like, a European model to look at it, but you can look up something called a spaghetti plot, and it will show you where all of the models say the track is going to go. So that's usually what I do, and I just, like, kind of see the general direction. And hurricane season has already started up for this year, so there's probably stuff out there forming right now. So the National Hurricane Center also releases forecasts for the entire year. So in 2019, they predicted it to be near normal. So there was 18 tropical storms. So it was an under prediction. Like, that's pretty high. They were saying that there was going to be 9 to 15 named storms, and there were 18. And they said 4 to 8 hurricanes, and there were 6 hurricanes. And they said 2 to 4 major hurricanes, and there were 3. So their other 2 forecasts were good, but there were a lot more tropical storms than they predicted that year. Can we go to this website? Oh. Oops. Let's see. National Hurricane Center, so you just Google it, click on it. No tropical cyclone activity expected during the next 48 hours. So yeah, as you can see, there's a bunch of stuff on here. Like, you can look at wind speed probabilities for different storms. They do stuff for each storm, but like, not much in our Atlantic basin, but you can click on the other things and see. So there's Estelle over here, and yeah, I think that the website is pretty useful. They have a lot of stuff on hurricane preparedness, and you can look at the arrival times of wind, and you can change it from earliest reasonable to most likely, and full forecast, or just 3 days, and you can turn on the wind speed probabilities as well. So it's a useful website. There's a bunch of stuff, so you can look at it later on when hurricanes start firing up. Okay, we're almost done. I think we are done. Wait, no, we're not. Okay, sorry. Got ahead of myself. Oh, look at this. Hurricane Katrina. That stuff, that was so nasty. Like, yeah, so the eye is calm. The eye wall is where the most severe thunderstorms, heaviest rain, and the strongest winds in the entire cyclone form. So yeah, so it's converging at the low, and it's moving around the low. So it's not hitting the low, like, it's moving around it because of the Coriolis effect. And so it's strongest around at the eye wall, but inside the eye it's calmer. So heavy rainfall can cause flooding, and the strong winds can damage structures, hurl debris, and blow people over. Tornadoes can occur in the eye wall of storms, although they're not particularly common here. I disagree. Like, if you get a strong hurricane, Mississippi and Alabama and Louisiana, Florida, Georgia, it's prime. Like, I had a friend who stayed for Katrina, and she lived in South Mississippi at the time. She lived right around here, like, pretty close to the coast. And her mom worked at a nursing home at the time, and so she was there. And they really regretted not leaving for Katrina. They had, like, tornadoes passing overhead, and the doors got blown out in the nursing home, and it lost its roof. So a lot of the damage from Katrina also came from those hurricanes that formed, or tornadoes that formed from it. So it's pretty, I mean, if you have this rotating motion and fast-moving winds, it's pretty easy to get weak tornadoes to spin up, especially with the major hurricanes. Yeah, so we didn't really discuss how the eye forms in the tropical storm. So what happens is like you have these updrafts that are moving up, but there's like this high pressure here. And so there's kind of like a thin area of sinking air aloft. It's going towards this low pressure. So it's trying to fill this low pressure in. So you have air from over here and over here trying to fill in the low pressure, but you also have this high pressure aloft that's trying to fill in this low pressure. So sinking air, it's like warming up, it's drying out. So this is unsaturated air, and this is what the eye is. So it's an area of sinking air that's trying to fill in the low pressure. Inside the eye, the weather is completely calm. I like this graphic. Spiral rain bands encircle the eye wall. Yeah, so there's usually they form in these bands, and they're like tens of miles wide, and they can extend 50 to 300 miles outward. So what happens is, yeah, you can get, this is kind of where you get the tornadoes. So air parcels rise within the spiral rain bands and sink in the downdrafts around them. So all of these have updrafts, so they must have downdrafts. So the downdrafts create sinking air. So you have rising air, sinking air, rising air, sinking air, rising air, sinking air, rising air, sinking air. So yeah, there's alternating areas of rising and sinking motion. So you can see that in here too. So like here, ooh, that's where my dad lives. Okay, so this is in Florida. I used to live right here in a town called Niceville. So we have like the sinking air right here in the middle, and then we have rising air in this main band, and this is where it's strongest. This is Hurricane Michael. I told my dad to evacuate, and he didn't. He really regretted that. I was like, dude, you need to get out. He's like, oh no, I'm fine. He has a freaking beach house. I was like, leave. But he did eventually evacuate. He evacuated. He was like here, and he evacuated over to Destin. But, you know, it's pretty powerful still. But, like, Panama City did not fare well in this storm. So, yeah, what happens is you have these concentric rain bands. So these are where the rising motion is, where it's like yellow and red, and the sinking motion is where it's green. But once it gets inland, it kind of slows down, and these rain bands kind of start spreading out. Like, they're not tight anymore, so it can kind of increase the range of places that get the storm. So they start spreading out. It's like an ice skater that's like pulling her arms together, and when she pulls her arms out, it slows down. So it just can't pull these bands in as tight anymore once it slows down. So coastal inland areas may experience more than one spiral rain band over the course of a day or multiple days, and this can lead to flooding and mudslides, and it's worse for those slower moving cyclones, because if it just parks here, it's just going to continue to dump rain. Here's a video if you want to watch it, optional. And this is the last slide for today, so thank you for tuning in watching. Again, thank you for your patience with my upload speed of this lecture. I know it is 11:30 in the morning, and usually I would have uploaded these the day before, but I hope you will accept my token of a extra 10% on your next quiz, and enjoy the rest of your day.